everybody, this is Lu from Edinburgh Napier University. This is the fourth episode of our video tutorials. Previously, we introduced the overall design of the Docker security infrastructure, the way of interacting with Spock client, the design and implementation of Docker's information sharing policies, and this time we are going to look into Docker's persistency mechanism, the data buckets. As shown by the picture, a data bucket is composed of two parts, the core data and metadata. Usually, each data bucket only holds information for a single attribute. For example, the bucket for blood pressure, the bucket for heart rate, and the bucket for body temperature. When a patient is being monitored, data samples are streamed to corresponding data buckets in real time. The core data part stores the value of data samples, and the metadata part stores descriptive information like who captured the value for which patient using which device at what location and at what time. It is very flexible to extend the metadata schema to preserve every possible environmental information that is needed by medical and data mining applications. Nowadays, the storage is getting cheaper and cheaper, and we believe it is worthwhile trading relatively more storage capacity for preserving what has happened exactly in the past. Next, a challenge after we have created a data bucket is how we can wrap it up and make it available as a data feed in a service-oriented architecture. A traditional approach is to publish a data source through a SOAP-based web service. In RPC fashion, a data consumer sends over a SOAP request and receives the data in a SOAP reply. At the server end, a bunch of web methods, as known as business or domain logic, need to be implemented. For example, to allow a client to retrieve data that has been captured by a certain individual, a getValueByCapture method is needed. Similarly, to allow a client to retrieve data captured during a certain period of time, a getValueByTime method is needed. When the business logic becomes fairly complex, you may end up with a sophisticated method like getValueByCapture and device and location and time. Just imagine, when the metadata schema scales up, considerable numbers of web methods will be needed to meet the requirement of highly flexible data mining applications. This could be very difficult to implement and to maintain. Comparatively, a better approach is to publish a data source using a RESTful web service. In a WWW fashion, a data consumer sends over a dynamic HTTP query and receives a dataset encoded in Atom or JSON format. Unlike the SOAP-based solution, a RESTful web service addresses data entities, links, and operations using URIs, and it provides rich option strings for a client to make up a specific query. A good example to understand how RESTful web service works in practice is the Silverlight OData Explorer. It is a web portal that exposes the well-known Microsoft Northwind database in a RESTful way. A sample query string may look like this. The invoice data table is addressed by /invoice, and option strings are appended following a question mark. In this example, the first option is a filter method, which requires the ship city column to contain a letter E. The second option specifies the result set is ordered by the ship country column. And the third option means to return only the first 5 records. Now let's try it out on the website. Okay, here we go. This is the user interface of the Silverlight OData Explorer. And here we can see a list of all the data tables of the Northwind database. And we visit the invoice table, ignore the error message. And you can see by default, the table is addressed as /invoices. Using the query builder, we can specify we want the ship city to contain a letter E. And you can see the first option string is appended after a question mark, and that is a filter using a method substring of. The ShipCity column contains a letter E. We click on the Go button. After a couple of seconds, we should receive all the results we want. Yes, a lot of records. We can append another query string, order by ship country. That is the column here, right? Now it is Germany. If we execute this query, the order of the records should be changed. Yes, it is. So ship country is Argentina now. So it is ordered by the ship country column. But we still have plenty of records. And we add on a further option string. This top 5. Yep. This gives us only the top 5 records. Alright, now we understand both the SOAP and the RESTful ways of publishing a data feed. The question is, which approach is better for Dakar? Well, by default, Dakar's security infrastructure assumes a service-oriented architecture is built up with SOAP-based web services, where XML messages are exchanged back and forth through reliable sessions over secure communication channels. Hence, SOAP is fully compatible with the current design, and the minimum effort is required to integrate a SOAP-based application to the existing infrastructure. However, as we have pointed out before, when it comes to the crude operations over a data bucket, SOAP can be overly rigid, cumbersome, and not scalable. On the other hand, though RESTful web services are more flexible, efficient, and scalable, the workload for fully supporting authentication, authorization, and data confidentiality can be considerable. As a result, we came up with a hybrid strategy, which is SOAP-based by nature, but supports highly flexible data queries just like a RESTful service. A client sends over a permission issued by the SPOC in the format of a data ticket, together with a query string, and receives properly anonymized and sanitized dataset from the data bucket. Dakar provides a unique query syntax. The syntax supports identifiers, literal values, and both primitive and complex data types. Also, the syntax supports arithmetic, relational, and logical operators. Another important feature is the support for variables. A variable is a keyword between two $signs. It can be a transparent ID of an object, which is converted by the SPOC into the corresponding opaque ID, or in other words, the pseudonym of the object at runtime. A variable also can refer to a value or a sequence number, of which the actual value is determined by the context where the variable is used. Last but not least, the query syntax supports chain of predicates. Each predicate is rounded up by square brackets, and the whole chain can be understood as multiple where extension methods of a LINQ query. These predicates serve as filters that gradually narrow down the scope of a result set. We cannot always connect the predicates together using the OR logical operator, because each predicate endows with a variable a different value. Here is a sample query. From the data captured by Professor Bill Buchanan after 12:30 p.m. August 24, 2010, retrieve the last 5 samples, of which the value is either greater than twice of the mean value or less than half of the mean value. Now let's have a look at how Dakar's data bucket works in practice. Right, now I'm in a client machine. As we have discussed in the second tutorial, before we can actually consume any application services, we have to log into the system and establish a secure VPN connection to the SPOC. In this demo, the user we use actually has a GP role from the Chelsea and the Westminster Hospital, because a policy rule has been set up that only allows the GPs to access the demonstration service. The communication channel is established. We can start up the client software. A common user interface for the Spock has been loaded. From the service provider drop-down list, we choose Chelsea and the Westminster Hospital because this is the owner of the service. The service name is called Example Bucket Reader. And now we are applying for the EPR of the service. The front end of the service has been displayed. For demonstration purpose, this service only interacts with one data bucket, that is the vital sign.heart rate. And here we have to specify which patient's records we want to retrieve. And I have prepared one patient. This is his login name. Connect. Okay, now we have successfully connected to the bucket. For the core schema part, we have one keyword called value, and it is of float type, providing three variables: the minimum, mean, and the maximum value. For the metadata schema part, we have an ID, that is an integer, providing two variables: the first sequence number and the last sequence number. Unit, time, capture, object, device, and location. All of the keywords here provided by core schema and meta schema, we can use them in a query string. In this text box, we can type any query string. A very simple example is ID greater than 50, for example. Submit the query. We got 147 results from the bucket. If we say we just want the last one, so we can specify we want the record of which the ID equals the last sequence number. We got only one result for that. That is the number 197 record. We can try a couple of other queries. For example, the value is greater than 100. We got 133 results. If we want to find out in this collection which is the first record, we can say ID equals first. And this chain of predicates give us one result, that is number 2. So number 2 is the first record satisfying value greater than 100. From this practical example, you can see it is very simple to interact with the data bucket, and it is very flexible to write any query string, and you can get exactly the data you want. In the next tutorial, I'm going to demonstrate how to program a software like this that is able to upload and retrieve data from a data bucket. That will be a very practical and interesting tutorial. So see you next time.